Let's continue from where we left off in the last video. I'll leave a link to the last video in the description box. AK will be our terms, and let's look at them as a sequence from k is 1 to infinity. And we will require three very reasonable, modest conditions on these terms. First of all of them are positive. And the next conditions that we have, AK is this sequence, AKK, is monotonic or monotone decreasing. Again, a very reasonable, modest assumption. And finally, the limit of these sequence elements as k goes to infinity is 0. Now we expect, that, okay, these things are getting small, so if we add them all up, monotone decreasing, yeah, maybe they'll converge. Well, let's see. For the usual series, sum them all up. Well, does this always converge with these nice three conditions on the terms? And the answer is no. It doesn't always converge, and we have an example that I did in a previous video. I'll leave the link to that also. This was the counter example. This was the sum of reciprocals, the harmonic sum. So this was sigma 1 over k. K is 1 to infinity. 1 over k is monotone decreasing. It's positive, and the limit is 0 as k goes to infinity. However, it does not converge as we saw before. When you compare it to log of x diverges, this diverges. However, alternating series is much better behaved. It's much nicer. And we see this does always converge. This is what we will prove. When you have these three conditions, this one, and this one, yes, the alternating series always converges. And it will always behave in the following manner, with this beautiful zigzag kind of pattern, and the partial sums start at 1, S1, S2. The even partial sums are at the bottom, the odds are at the top, and it converges. And this one was our example that we used, -1 power k plus 1 over k. K is 1 to infinity. And this converges. I asked you, what do you think this number is? Well, it turns out this number is log 2. And so that's very interesting. We can use that for an exercise at the end. So here I have done a total of 40 partial sums, and here too from S1 up to S40 I plotted them just so you can compare. Now all alternating series will have this kind of behavior as long as the three conditions on the terms are satisfied. It will behave in this beautiful way, jumping up and down around the limit, the sum. That's very beautiful. Okay, so let's prove all this stuff. So let's prove some things about the even partial sums. An even partial sum, as you recall, has an even number of terms. First of all of these are greater than or equal to 0. That's one thing we will prove. As a sequence, these even partial sums are monotone increasing, so I put an arrow up to show that. And all these partial sums, even partial sums, are bounded from above by the term A1, the first term. So let's get to this. Let's start with A. Let's write A1 minus A2 plus, let's do this, A3 minus A4 plus plus A2n minus 1 plus or minus A2n. Now we can group these things like this. And because AK is monotone decreasing, monotone decreasing, that means that this is greater than or equal to 0. This is greater than or equal to 0. And this is greater than or equal to 0. Very nice. So therefore, S2n is greater than or equal to 0. So great, we have this one. We did this one. Now we have to go for B, monotone increasing. So this sequence S2, S4, S6, and so on, this is increasing sequence. How do we prove that? Well, we'll take two terms, S2n, and then the next term, S2n plus 2, and then we will compare them and see. This is what we want to show, that S2n plus 2 is greater than or equal to S2n. If that's the case, then it's monotone increasing. That's the definition of monotone increasing. So here I've written the whole thing out for S2n plus 2. And let's look at what we have. Well, I have all of this. This is S2n. That's that partial sum. And then on the outside, all the way up here, I have S2n plus 2. So I can subtract these two. S2n plus 2 minus S2n. And what's that? Well, it's what is left over. And that's these two terms. So that's A2n plus 1 minus A2n plus 2. However, AK as a sequence, this is monotone decreasing. And so because it's monotone decreasing, this has to be greater than or equal to 0. So if that's the case, therefore, S2n plus 2, the next even partial sum is greater than or equal to the current partial sum. And we're done for this. Very nice. We did this one. Ta-da. And now we just have to prove that S2n, the even partial sums are bounded. So S2n bounded from above by A1. Okay, so I can start by writing out some terms. Okay, there we go. So I wrote all these terms out explicitly all the way up to A2n. And now let's do a bit of algebra here. Let's factor out the minus. So I have A2 minus A3 minus A4 minus A5 like that. And so on and so on. I factor this out. A2n minus 2 plus A minus A2n minus 1, and then minus A2n. But as you recall, very important, our sequence of terms is monotone decreasing. So that has interesting implications. This number here is greater than or equal to 0. This is greater than or equal to 0. This is greater than or equal to 0. And this is actually greater than 0, this number here. Why is it greater than 0? Because in the conditions on these terms, each term is greater than 0. That was the first condition. So what I have here is this is a positive number here, greater than 0. And I'm subtracting all these numbers which are greater than or equal to 0. So if I actually don't subtract them, what happens is that this has to be bigger than S2n. And so therefore, I have what I want. S2n is bounded from above by A1. But we can see all these things in a picture. Let me show you. I think I have enough room to show you. You can see it all here. This is A1 because S1 is A1. All right. So these terms, this is S2, S4, S6, and so on and so on. All of these terms are bounded. All of them, they're as far as they go, of course, they are bounded. S2n is bounded by A1. And we can also see that S2n is increasing. Very, very interesting. So we see the behavior in this picture. It really helps to draw this picture, because if you don't draw any pictures, it's hard to imagine what's going on with this alternating series. Once you see this picture, then all of the theory of alternating series makes sense. And without this picture, I think it's much more difficult if you're studying this. The odd partial sums have similar properties. Recall that an odd partial sum is one that has an odd number of terms. So we have, like with the evens, the odd partial sums are always greater than or equal to 0. That's the first point. The second one is that the odds, when you view it as a sequence, S5 and so on, this sequence, S2n minus 1, decreases. It's monotone decreasing. It's the evens were increasing, if you recall, but the odds will be decreasing. And finally, the third property is that they are bounded. They are bounded from below by A1 minus A2. So that's very interesting symmetry with the evens, if you compare it with the evens. I'm leaving this as an exercise for you to do. I want you to really try and do this. It's very interesting. It's not because I'm a lazy bum and I don't want to do this. But I mean, I've done this, but I just want you to do it. It's just really interesting and enlightening if you go ahead and prove these three things. The method of proof is very similar to what I did with the even partial sums. And to help you along a bit, I'll just talk a bit about this using my picture here. So this is S1, and S1 is A1, and S2, that's A1 minus A2. So it's obvious from this picture, although it's not a proof, you could just visualize it using this. We proved the following things from before. We proved this is smaller than or equal to A1. This is true. I mean, obviously, the greens are the S2n's and the blues are the S2n minus 1. The greens are the evens. So the greens are all below A1. That's pretty easy to see. And this part C here, this tells us that S2n minus 1, this is always bigger than A1 minus A2. How can we visualize that? Well, those are the odds. That's this. They are always bigger than this one. Okay, so easy to see. So those two make sense. But we can just as well add, I can complete the picture and say this. This should also be true. And this should also be true. But just look at it. Everything is bounded by A1 and A1 minus A2. Everything is in between this interval. So that's actually very interesting. And this I want you to prove also as another exercise. This is very interesting. So prove this part and prove this part. It's not hard to do. It's the same techniques. It's very nice proof. And keep this picture in mind. With this picture, you won't be confused about what's going on. Now it's very easy to prove that the limit of these partial sums exist. The evens are monotone increasing and they are bounded from above. And so by the monotone convergence theorem, this has a limit. It must have a limit. The limit exists. So limit S2n as n goes to infinity. This is something. We can call this A. That's guaranteed by monotone convergence theorem. If you don't know what monotone convergence theorem is, well, just hang in there. I will end up doing a video about it probably soon, since I'm kind of into those topics these days. Similarly, the odd partial sum sequence is monotone decreasing, this sequence, and this is a sequence. And it's bounded from below, so monotone convergence theorem applies. Yes, good old monotone convergence theorem. What would you do without the monotone convergence theorem, really? It's really one of the most important theorems in mathematics. This limit exists, and we can call this B. Great, so let's subtract these two. We want to prove that they are equal, so we will subtract them and show that they are equal to 0. So that's limit as n goes to infinity S2n minus limit as n goes to infinity S2n. n minus 1. And we take the limit out like this. Now, you just have to think a bit. The last term here in S2n, the last term is minus a2n. So all of the terms before get canceled out because I'm subtracting them away, and the only term left is minus a2n. So then this is limit n goes to infinity minus a2n. And this, of course, is 0. Because, why 0? Why 0? Well, think back to our conditions on our sequence of terms, a, k, k. This sequence, well, one of the properties, property C, k goes to 0. This is 0. The limit of the terms, the sequence of terms is 0. And so therefore this is 0. And let's go back to our diagram and look at it. We see that the odds, S2n minus 1, yeah, they tend to the same limit that the evens tend to, as you can see. Well, we proved this mathematically. The picture doesn't really prove it, but we proved this up here, that it's true. Okay. And furthermore, Sn, well, what is limit of Sn as n goes to infinity? Well, okay, Sn is either, if n is odd, then okay, actually, let's just call it k, just to disambiguate this. If k is odd, then it's going to be up here somewhere, sk. If k is even, then it's going to be up here. Here k is even. If k is even, then sk is going to be down here. So either way, it's tending to the same limit. Okay, so we showed above here that limit of S2n equals limit of S2n minus 1, and we can call that big S, all right, with no subscript. So that's the limit that the even and odd tend to the same limit. Well, this has to tend to the same limit also, because as you see here, it's either one or the other. Okay, I find that this argument is sufficient. It's convincing, but if you want something more formal, I can suggest a few things. You can try to formulate this argument using the squeeze theorem in analysis. It amounts to the same thing, but it looks better. Or you can use lim sup and lim imp. This also amounts to the same thing. And but it's more rigorous way of describing what's going on. So, but I think here we don't have S in the middle somewhere. That's not the case. It's either up or down. Sk is either up or down, depending if k is even or odd. Both of them tend to the same limit, S, and so therefore this must be true. Okay, there you go. And so therefore, we've done it. Therefore, this alternating series, minus 1, k plus 1, ak, this limit, or this sum, equals S. It does have a limit. It always has a limit. If our terms satisfy those reasonable conditions, modest and reasonable conditions, then we have a limit, and the limit exists. And there you go. I think that's a very, very beautiful proof from analysis. Everyone should know this. And now for a really elegant result, we have this truncation error estimate for alternating series. Suppose you have this alternating series and it has a sum, it has a limit, and the limit is S, the sum is S. So how good is the following partial sum, let's say S10? How good is that as an estimate for S? Well, we can actually get an answer to that question. Suppose k is even. Then S minus sk is positive because sk is approaching S from below. So we can get rid of all these terms, the first k terms, and we're left with ak plus 1 minus ak plus 2 plus ak plus 3 minus ... Okay, and why is it plus here because k is even, k plus 1 is odd. So the first thing to notice is that this is an alternating series. Alternating series. So it has a sum and a limit because the a, k here have the same properties that we want, that ensure the limit exists. And furthermore, we know that the partial sums of this are bounded. So the partial sums, I don't want to call them S because S are the partial sums of this thing. So I'm going to call them C. So C and are all bounded by the first one, a, k plus 1. And this is something we proved before. And as you know, if every partial sum, if every term in a sequence is bounded less than or equal to something, then this is true also for the limit. So limit c n, this is less than or equal to a, k plus 1. So it goes to infinity. And this means this whole thing here is less than or equal to a, k plus 1 because of this. All right, so we got part of our desired result. S minus sk is less than or equal to a, k plus 1 when k is even. So what happens when k is odd? So suppose k is odd now. Well, the odd partial sums are above, so we want to subtract it this way to get something positive. And this will kill off the first k terms. I have a minus here. Okay, so this is minus a, k plus 1. Why minus a, k plus 1? Because k is odd, k plus 1 is even, so there's a minus in front. A, k plus 2. There's just so much to think about. A, k plus 3 plus ... And likewise, the same kind of reasoning here. First, let me distribute the negative. I have a, k plus 1 minus a, k plus 2 plus a, k plus 3 minus ... This is an alternating series. It has a limit, it has a sum, and it's also bounded for the same reason, like this. It's bounded, so the whole thing is bound. Every partial sum is bounded by a, k plus 1, so the limit of all those partial sums is bounded by a, k plus 1. So I have this. So if I combine, I have this guy, and I have sk minus s less than or equal to a, k plus 1. I can combine the two, and I have s minus sk is less than or equal to a, k plus 1. Doesn't matter if it's even or odd now. So that's a beautiful thing, and I'd like you to play with this. I'll show you what I mean. Take our alternating harmonic sum. This has converges to a limit, so it converges to its summable. This s is log 2, and I want you to take the 10th partial sum. And how good is this? So verify this, this s minus s10. Is this less than or equal to 1 over 11? That's a11. Is this true? And try it for s20 and more if you can. This is doable with your favorite computer programming language. And try this. I tried it. It's quite interesting to play around with this. Well, that about wraps it up for alternating series. Now I can move on to proving some spectacular theorem, which is coming very soon, probably in the next video. And I will see you next time.